Okay, start recording and maybe explain. So today I want to finish the proof of Margulis of Borel Harish-Chandra theorem. So we did all the preparation and now we can just complete the proof. So let me recall what we did in the last 2 weeks. So first we did we put the following theorem. So okay, we assume there are several assumptions. So G acts on X. X is the nice space, proper, locally compact, mu probability measure on G, sigma measure on X, and we suppose that there is no non-constant L2 invariant function on X, so which are so there are no non-constant function, non-constant in L2 X sigma, which are invariant under the support of mu. So that's one assumption. Then we had several other assumptions about the action and the measure.
In practice, you assume that the support generates, so it's G invariant, right? In the end,
we suppose the following. Suppose there exists, that's the main assumption, a function f from X to R, and that's what we call a Margulis function, which is proper. That's most important, such that n to constant C a constant which is smaller than 1, and B, let's say another constant, positive, but we prefer it 0, but such that the convolution of mu with f is smaller than C times f with B everywhere at any point. So f is proper and satisfy this condition. Then the conclusion is that the measure is fine. So this we did 2 weeks ago. From the mock approach. Then last week we proved that if mu satisfied, so this we had last 2 weeks ago, and last time we did the following. Suppose u is satisfied three things. So okay. Now we assume for the moment let omega n, that will be X for the moment, will be SLN R mod SLN. and sigma is the Haar measure, with the measure induced from Haar on this space. So this is the space of lattices in Rn. So we consider this. I just remind you things we did last 2 weeks. So let rho from G to let's say GLN or SLN be representation, and we suppose the following thing is that assume in addition that mu is symmetric, compactly supported, mu is compact, and the support of mu is compact, and rho of H is inside what is we denoted by S close of Rn, which is the set of positive definite matrices. Symmetric matrices which are positive definite. Or of, yeah. Support is such. And we also want that it's irreducible. The group generated by rho of support mu acts irreducible with no invariant vector. Then, okay, there was a lot of notation and so. And then under this condition, so theorem or supposition, okay. Under this condition, there is f on omega n satisfying the condition the theorem. So maybe we call this theorem okay. So that's what we did 2 weeks ago, and this what we did last time, and it was like some sophisticated, some very tricky function using this what they call alpha function. It's like weighted sum of the alpha function. Anyhow, we have this. What was the question?
Guessing the image of Y is closed, or it doesn't know?
The image of?
Oh, doesn't know.
It's automatically closed. Achieving.
Yeah, that's understand.
And so, and the conclusion so far from this proposition and the theorem is that SLNV is a lattice in SLNR. So sigma of omega n is fine.
So you apply your G plus SLNC.
So yeah, in particular, you can if you yeah, you can take G to be SLN R, and the X to be space, and then just you have to prove that it can be generated by quality indefinite matrices, which is the exercise. You take some measure, just some compact sets of quality indefinite matrices, generating SLN R, and then yeah. Let me just, so this is an immediate corollary. Let me write something more general. I just wanted to remind you these two theorems. And now we use much more general. So we use that every arithmetic group in every Q algebraic group, which is semi-simple at least, is a lattice. That's the aim of today. So there should be, the master students have some meeting at 12. So I don't know, one option is just we do continuously up to 12 and finish then. I hope I will finish the proof. Another option is that you go late to the meeting. I don't know what is it. I mean,
12:30, I think it will be over.
it's obligatory, like they will cut your scholarship if you don't. Yeah, okay, let's try to do, maybe it's not that much, maybe you can do it. So here is the proposition. So actually, it's a sequence of 4 or 5 statements. So position G inside SLMR be a closed subgroup, closed, connected, semi-simple, or it's irreducible, semi-simple, with no compact. But let X be a point inside omega n, and suppose that the orbit is closed. Then UG, I don't know if it's a good notation, call it sigma G. Then sigma G of GX finite, where sigma G is induced from R in G.
Why don't you just say that the stabilized offset is a lattice, then it makes the word saying it's
you can, okay, this is what I want to say. I copied the statement from the paper, and yeah, it will follow that the stabilizer of X is the lattice units. And the proof, okay, so Paul said that there is a gap here, but I'm not sure. I'm referring to most of the theorem. So the proof.
Sorry, omega n is the quotient of SLN now with G or with SLN Z?
Omega n is the space. Omega n, by definition, is the space of unimodular lattices in Rn, like the n, and we identify it with SLNR. SLNR acts transitively on unimodular lattices. Unimodular modules are covering with one. And the stabilizer of Zn is SLNC. So you can identify it with this quotient. So this is omega n, and now I look inside omega n on orbit of a closed semi-simple group. Yeah, I don't like this at the moment. Still, I'm not even saying that G now is rationally defined and so on. So I just say that it is closed, and assuming it's closed, then you can push the Haar measure to the orbit, and you get a finite measure, and off it does follow. So by the theorem of Mostor, which is very useful theorem, you should be aware of. This is a special case of it. Since G is semi-simple, there is G in SLN such that the conjugation by G is adjoint invariant. So let's assume that G itself is already adjoint invariant. Replace G by this conjugation and it's adjoint.
Sorry.
Yes.
So the sigma G of the orbit is just, you said, like sigma G on the orbit is to push forward of the Haar
Yeah.
measurement. So
It's not a push forward.
Not a
No,
push
no, it's not
forward.
a push forward.
It's
You
not a
intersect
push
it with
forward.
a fundamental domain.
It's a it's
There is an invariant measure on
Ah.
Gx because tab x is unimodular and G is unimodular. The
So-
question is whether it's finite or
Okay.
infinite.
yeah, sorry, it's
the
Yeah.
stabilizer.
That's what I said.
The stabilizer of X in G is the intersection of the stabilizer of X in SLN with G, which the stabilizer of X in SLN is the conjugate of SLNZ. So you intersect it, and then so you have a discrete subgroup, and then you can play the game there. Take the fundamental domain and
What does it mean joint invariant?
for SLN that joint is just the transpose.
But when-
Transpose invariant.
I as a set. Okay, when you do okay.
G is on joint. So suppose that G is so this suppose we can change it, and if you want to replace X by G times X, then but well in this situation. Then so that's a fantastic theorem of Mostor. It's very, very useful. In a sense, it's also a geometric interpretation, which I like. Okay, let's not. I feel a bit that I need to hurry because of this Vadat Torah meeting, and I want to be done with Borel and Harish-Chandra today. What other things? So let's go on. So this then such group. Then you can prove, it's not hard to show, one C that G is generated by a compact subset of positive definite matrices. So if you have, that's an exercise which I don't want to do now. I think you can find similar exercise in the book. If you have such a group which is transpose invariant and without compact factor. Here we use the fact that it has no compact factor. Then it can be generated by. So we can choose. To choose a measure on G. A probability measure on G satisfying the condition that we just erased. Needed the conditions that was before. Here. It's cool. So the condition that we need, it's symmetric, it's by positive definite matrices, probability measure, and it generates G. So G is irreducible. That's the assumption. So we can find such a probability measure on G, and then by the theorem. So by the theorem, Lewis proposition. Then by the proposition. F is what we call the Margulis function. F satisfying the same F as before. Mu convolution F smaller than C times M plus B. I mean that there is for some B and C with C smaller than 1. And therefore by the theorem we have the result. Sigma G of the orbit. Okay, that's so we use the fact that it has no compact factor to say that it can be generated by positive definite matrices, and this was somehow crucial. The proof, all the proof seems to use so little, like only Cauchy-Schwarz. At some point at the beginning, we used Cauchy-Schwarz, and for that we needed that the measure is symmetric and generated by positive definite matrices. And if you follow what we did in the last 2 weeks, so that's all we did. It's very like okay.
What? So it was. I think it's easy to choose such a measure. It's not.
What?
It's easy to find such a measure. And use the transposing variance just to find a compact set of positive definite measure that we generate.
In fact, you can take the measure to be even, the measure could be actually generated. You can take 2 elements and the inverses, and we can take just the Dirac sum of Dirac measure. That would be this measure that you use. It's very, very elementary.
Just like any measure on the compact set.
Any measure which is symmetric can generate G, but you can do a measure that it's supported on 4 points. Okay, so that's you see when we are approaching Borel Harish-Chandra. The second lemma that we need is the following. So let G inside SLN be a Q algebraic group, Q subgroup. So it's defined over Q. It's an algebraic group. It's a zeros of polynomial with rational coefficient without no Q character. So there are no. In particular, if it's semi-simple, then it's fine. But even if it's not semi-simple, but there is no Q characters, it's still fine. So it's a rational group. So now then the map from G mod GZ to SLNR mod SLNZ, which we call omega n, is proper. And in particular, the image is closed, and the orbit of G of R times X is closed. Well, X is the point the end.
Why is this particular?
An image of a proper map is closed.
The image.
Yeah. So this map, yeah, I mean, this space I can think of it as, yeah, this space, I think of it in two ways, like as a quotient space or as the space of all lattices. Just the image of proper map is both. When it comes to group, when it comes to space, and okay, the book is properness of this map GR mod GZ to SLNR mod SLNZ is equivalent properness of the map SLNZ mod GZ SLNR mod G. Meditate on it for half minute to see that it's the same. I mean, what does it mean that this map is not proper? Let's say this way. Not proper mean I can go to infinity here, but stay bounded here. Go to infinity here means I go to infinity, but stay close to GZ. While here, sorry, go to infinity, go far away from GZ. While here, I stay close to SLN. So it's exactly the same. So if I stay close to SLNZ, I can move into SLNZ, and then I go to infinity in SLNZ and go away from GZ. So go to infinity here, but stay close to what was before here. So okay. I don't know what a better way to say that, but this is
You just say it again.
yeah. I said, but you will miss the middle. Right, so I said that this map is proper, it's the same as saying that this map is. So I want to think of it to show that this is not proper if this is not proper. So what does it mean that it's not proper? It means that I can go to infinity here, but stay bounded here. Go to infinity here means inside G, I go away from G. But if I look here, I stay close to SNC. since I'm close to SL and Z, I can move a bit and be inside SL and Z. Not anymore in GR, but close to GR, because I moved a bit. So what does it mean? Now I'm in SL and Z, going away from GZ, so I go to infinity here, but I'm still close to GR, so I stay bounded here.
The idea is clear, but it's very not clear why you can actually be in SLNP.
You
can just move it.
I move a bit. So I have two orbits. I have like the, let's say, a black orbit, which is go to infinity here, but stay bounded here. And then near it, I pick a blue orbit. The blue orbit is the one in SL and Z, which is close to that. So the blue orbit is in SL and Z. It's close to the black orbit. The black orbit go away from GZ, so the blue orbit also go away from GZ. But it's close to the black orbit means that it's close to GR. So it's a bounded. Okay, you need to meditate on it and explain it to yourself in your own world. I think I don't know what else to say. Anyway, so now I apply a Chevalier theorem. By Chevalier theorem, I don't know how to spell Chevalier, and so someone needs to help me.
B-A-L-L-E-Y.
There is a Q representation, there is a rational representation, a Q representation, rho from SLN to some other group, some, let's say, GLW. It's a rational representation, such that, and, okay, GL, let's say, W, and a vector W0 in, let's say, GL RM and W0 in QM, so it's a rational vector, such that G equals to the stabilizer of the line. So G equals to all G in SLN, such that G W0 belongs to the line R W0. So that's Chevalier theorem. So every algebraic subgroup of algebraic group there is a representation such that it's a stabilizer of the projective point over a line. And you can do it over the field Q when the group is defined over Q. Now I use the fact that there is no character, since G has no Q character, we see that G is exactly the stabilizer, so SLN R is exactly the set of all point. Here, it's exactly the stabilizer. It's exactly G in SLN, such that OG W0 equals W0, not just proportion equals W. Otherwise, if it wasn't equal, I would get some character of OG.
You mean the map from G to R that tells you what is the scalar you need to multiply would be a Q.
Yeah. So that's okay. And now see that you see that G is exactly the stabilizer of W. So now, so this allows us to identify SLN Z mod GZ with SLN Z times W, and here I act via rho because GG is exactly the stabilizer, and SLN R mod GR with SLN R times WC. So the properness of, let's call it snap psi. So properness of psi becomes clear. So there is something hidden here, I think. The orbit, the SLN-Z orbit of W is discrete. Let me say something. So you need some background from arithmetic book here. Maybe I should. I also need it for the next proposition. So let me do it. I will write the statement, and you tell me if you can leave it as an exercise or you want to explain it. It's something that's important, but in elementary. So let's say proposition. G and H be Q. Q algebraic groups. What do I mean by that? So you can, so G is a subgroup of GLN, H is a subgroup of GLM, and each of them is given by each again is the zero is a set of common zeros of set of polynomials, finitely many polynomials which are with rational coefficients. That's a Q group. So let rho from G to H be a Q map, Q morphism. So it's a map which is a homomorphism of group. We need to find over Q, so the rational coefficient. Then for some M in Z, the M congruent subgroup of GZ is mapped into HC. That's the proposition. And the corollary, which is corollary.
Very stupid question. So it's not true that GZ is mapped into HC?
No.
Somehow I got the feeling that is true before when we talked about GZ and SLN.
You can
No,
take a conjugate.
but the corollary, so let me write the corollary. The corollary is what?
You can take like the map from SLN Z to SLN which is conjugation
Yeah,
by a Q element.
conjugate
Q map.
SLN Z by some rational. So the commensurator of SLN Z is SLN Q, but it's not normalized. So the corollary is the following. The corollary, if rho is Q isomorphism, then we deduce that GZ, that rho of GZ is commensurable to H. And one, yeah, so in particular, take SLNZ and conjugate it, the map, the rational map by conjugation, conjugate by element in SLNQ, you get something which is commensurable, but not necessarily equal, or it won't be. So the normalizer of SLNZ is SLNZ, it doesn't have the. So if you want, I can explain the proof. It will take maybe 10 minutes, but then still since we are rushing a bit, let me just tell you the proof, okay? Let me tell you the proof without like hand waving. So what does it mean to be a rational map? It means that okay, it's a map. Let's say it's a map on the entries here, find on the entries, and to the entries into let's say GLM, and so it's polynomial in the entries. So like M square polynomial, the map is given by M square maps. Each of them is rational, so it's polynomial in the entries. Now, if you write it, if the entries are xij, then you get polynomial. You get a C LK. You consider maps like that in the variable xij. Now let's change the variable and view xij. Some of the variable I want to leave, but the diagonal variable I replace xii with xii minus 1. I think of it as mapping xii minus 1. Okay. Basically, I want to say, okay, to do it formally, it will take a few minutes, but so there is some common denominator, and there is some, and okay, all the coefficients are integer, are rational, but all of them are integer divided by some common m, let's say. And so if you consider those which are 0 modulo m, the image will be consistent with integers. That's it. Okay, let me leave it as an exercise. And if you want, I'll give you more details after. I just
Like the reason this is not a positive because of the diagonal, you're not divisible by m.
no, because it's a morphism, it sends the 1 to 1. It sends the diagonal 1 to the diagonal 1, and therefore you can think of it as, therefore you get a map which consists of polynomials which are homogeneous. There is no free term, and okay, I think you get it. Anyhow, so this is important here, and now we can actually we're very close to the end, so maybe I can explain this in more details. So let's see. After the master student leaves, which I think they are the only one who didn't see it yet, but watch the video. So proposition.
We can go to the meeting instead.
Yeah. Okay, so let G be connected semi-simple Q group such that G of R has no compact factor. Suppose G admits a faithful Q representation which is irreducible over R. Then GZ is a lattice in G. And okay, I think just combine everything we saw before, right? So you have
Okay, so we understood the signal is acting visibly on our line.
okay, you have subgroup. Suppose that rho from G, G is GR, to let's say SL and R. This is a Q representation. Q faithful representation. And now you know by H denote the group rho of G. By the plus proposition, then rho of GZ is commensurable to H of Z. So it's enough to show that H of Z is a lattice in H. And okay, this we already know by the lemma that we just raised. H mod H of Z is closed, and by the proposition which was before, we deduce that by the lemma, maybe I should have given the number. By the lemma, H mod H Z side omega n is closed, and by the first proposition, they we deduce that HC is the lattice. Okay. Now, you write that we could formulate it in the beginning, like saying that, yeah, but when we just stated the first proposition, we didn't even assume that the group is rational. Okay, so this somehow takes care of almost everything. Now when we have Okay, now I can prove actually Borel Harish-Chandra for semi-simple.
You mean with convex factors? Is that the difference?
Yes, yeah. No, what do you mean? Yeah, so yes, so somehow so far we wanted that okay, let me maybe the proof will clarify. So you write it as corollary, but let me write it as a theorem. So that's more or less Borel Harish-Chandra theorem.
Tsachik, yeah, the representation doesn't need to be faithful, right? Here, because we can also use commensurability in G. So it only needs to have finite kernel.
Sorry?
The rep only needs to have finite kernel. It doesn't need to be faithful.
Yeah, you're right. Yeah. But let me write the theorem, Borel Harish-Chandra theorem, is the following. So it's still not the most general version, but it's for us it's good enough. So let G be an adjoint group. Connected semi-simple Q group. Then, okay, the volume of GR mod GZ finite with respect to R on G. And again, it's not a push forward of, yeah, it's a measure coming from the R restricted fundamental range. Okay, let me write the proof and you will see. So we did all the work. Or maybe before the proof, I should say something about the difference between isotropic and non-isotropic. And if you have a group which is defined over a field, it is called isotropic if there is a tori of positive dimension which is defined over the field. Equivalently, it's isotropic if and only if there is a unipotent element in the field. So G is Q isotropic if and only if a GQ contains unipotent element. It's related to compactness. So if you consider a group over a local field, if G is a group defined over K, so G is isotropic over K if and only if it is not compact. So anisotropic groups over a local field are exactly the compact. Here in the Borel Harish-Chandra theorem, in arithmetic group theory, to say that GZ an anisotropic lattice is exactly for compact. You will see it in the proof. So G is anisotropic. Okay, so in the proof we can assume that G is QC. That's like that's the irreducibility assumption. If it's not, then it's a product of Q group, and then you take care of each factor separately. So that's we may assume that. So we start with the fact that it's QC. Like so you know what I mean by that? QC. For example, we spoke an example of restriction of scalars. So we spoke, for instance, of SLN, SLNZ, SL2, say. We had this example, something, V square root of 2, which is not a lattice in SL2. But then we did a restriction of scalars and embedded in SL2R cross SL2R. Remember, we did some restriction of scalar, and here it sits like one time like that and one time by the Euler conjugate. But if you think of this as G, then the image of that, this will be GZ. This will map to GZ. So this will be a Q group. There is a Q, but not the one we see, not the one we see, not the product one. There is a Q structure here such that this is exactly GZ. So this group is Q simple.
Means it's in the direct product of Zariski closed subgroup?
What?
You mean that it is not a direct product of Zariski closed subgroup?
In particular, it's not a direct product of Zariski closed subgroup. There is no, yeah, GZ, it will be irreducible lattice.
I don't mean GC, you say Q simple, you mean not a direct product
Yeah.
of Zariski closed?
Not a direct product of Q sub. Yeah, there is no normal Q sub. But I just want to explain the notion. So this, the group that you get from SL2R by restriction of scalars from Q square root of 2 to Q is not R simple, but it is Q simple. And this is what we need here. It's just an example, so you know what we're talking about. And then there are two cases. Suppose first, suppose that first that G is Q and so there are no, in particular, there are no Q unipotent. Consider the adjoint representation. G to GL of the Lie algebra and take a Z lattice, a rational lattice, a Z lattice in, if you want, GQ. The algebra, you take a Z lattice, call it A. Okay. By one of our proposition, we proved that then the orbit of L, the G orbit of L is closed. But I claim that it is also compact. Not just closed, but it's compact. What? This sits inside the orbit. Let's open the orbit G times L inside omega n, where n is the dimension, is closed. I want to claim that it's compact. Note that the characteristic polynomial so any element in L is a matrix. The characteristic polynomial of any element in L is with integer as integer coefficient. Right. If you want L, you can think of L as we can think of L as GZ actually. With respect to L, I can think of L as the Lie algebra, something like that. I think it's well, fine. Okay. Now that's a remark. Now G has no unipotent. L has no nilpotent element, except 0, no non-trivial. That's an assumption by the anisotropic assumption.
You mean at G.
What?
L or at
L, the Lie algebra does not have to say that G has no Q unipotent is the same as saying that the Lie algebra has no Q nilpotent. A unipotent, the logarithm of a unipotent is nilpotent and the exponent of nilpotent is unipotent. So to say that G has no nil, so there are no nilpotent, that's exactly this assumption. Assumption that is anisotropic exactly give you that. Therefore, Z to the N is not a characteristic polynomial of element in N.
See, like not
small
Z to what?
small
רק ה-Z שיהיה לו אינטג'ר.
Yeah. X to whatever, to the right dimension, maybe not 10. X to the D. It's not polynomial. This is the dimension of matrix. No, N. Maybe I'm confused with maybe N is not the. Okay, I'm confused with the dimensions here, but X to the N is not a characteristic polynomial. And therefore, this implies now Mahler compactness criterion implies that the GL is relatively compact. Is compact. Because we already know it's closed by previous proposition. Now we know that we cannot, you remember a set of lattices in Rn is not compact if and only if you can find a lattice which intersects non-trivially and arbitrarily small neighborhood of 0. Now, so if this orbit of L was not compact, we can find a matrix in some in the orbit of N, we can find a non-trivial matrix which is very close to 0. But then its characteristic polynomial will be very close to that one. But it has integer coefficient, so it's exactly that. But then it will be it's an important element. But you don't have. So that's Malloc compactness criterion tell you that the orbit is compact, hints, which implies that yeah, so in that case, that yeah, that the GZ and G are Margulis give credit for his argument to most of it. With I think about the same time that Borel and Harish-Chandra proved their theorem, Mosto and Tamagawa wrote another paper proving it's about only about the anisotropic case. They showed that basically the easier case of Borel Harish-Chandra theorem, which is exactly that. If G is Q anisotropic, then G is co-compact.
So when you think about co-compact lattices, say classic example of SL2R times SL2. How do you see that G is K anisotropic in this case?
It must be, because if it's not anisotropic, then you have unipotent in GQ. Now GQ sits diagonally, it sits faithfully in each of the real factors. So, and compact group don't have unipotent. So let me just now finish the proof, because we are very close. We did all the work already. Most of what we did was for, okay. So let me just finish the proof. So suppose now that G is isotropic. Suppose now G is isotropic. Then what was the idea? Then consider the product of it's not simple. So consider product of R the simple factor for each for each simple factor, consider the adjoint representation. The adjoint representation. I should say something before that. In that case, G has no compact factor. In that case, G has no compact factors.
So aren't we done?
Yeah, we're done, but let me say, I want to deduce to the statement that yeah, it's two lines. I just was consider the for each the adjoint representation and take the wedge or the tensor products of these representation and we get a Q irreducible representation and deduce this is defined over Q and irreducible. So we deduce the result of previous.
Second, by if G is isotropic, we inject no compact factors.
If G is isotropic, so there are two. What is isotropic group? So a group is isotropic if I can say two things. If one way, usually people say a group is isotropic if there is a tori which define over the field of positive dimension. But it's equivalent to say that a group is isotropic if a semi-simple group is isotropic if and only if there is a unipotent element in the rational field. So the group now I assume that it's Q isotropic. We assume it's Q simple and it's Q isotropic. So there is a unipotent element inside G of Q. So G of Q contains some unipotent, which is non-trivial. So now this G of Q embeds in any, so the embedding of G of Q embeds.
Saying no compact factors is like saying no R anisotropic factors, right? So you.
Yeah.
So the same. Okay. So
yes, but it's the same. But since we assume the G is simple, Q simple, then the simplicity is the irreducibility of the lattice. So GQ embeds into
injectively into each real factor.
Yes.
But
the real factor are just a Galois conjugate of a given of each other, and that's actually how the way to see that this tensor representation is defined over Q. Yeah, okay. For me, that's good enough, I think.
And when you set for each simple factor here, it's for each simple real factor.
Yes. Yeah. So it's, yeah, which, yeah. So in that case, G of R has no compact factors. Let's, at least for completeness, state the general version of Borel Harish-Chandra. In the paper, Margulis do another page and a half to prove, to deduce this, but I will not do it here. And again, he refers to, he says that it's all, the argument is due to Mostov and Lamagava. He needs to take to deal with reductive group or with semi-simple group which are not adjoint. So the general theorem is stated and Harish-Chandra let G be a connected Q simple group. A Q connected Q group. So it's the Zariski connected Q group with no non-trivial Q current term. By the way, if you follow the proof that we presented, the Margulis proof, it's very clear where he used the fact that there's no Q current. It's only one statement that assumed it. Then the volume of GR mod GC is fine with respect to R. Space is the only measure. And you can go on and say that it's compact, this space, if and only if it's not, if and only if it's not, it's in G, it is Q anisotropic. And okay, it's a bit technical. I don't want to do that.
Give an example of the Q character which is this one.
Yeah, very nice example. The diagonal group in SL2R. It's a one-dimensional group defined over Q, but its Z point is the trivial group. So it's overlaps. But also, to deal with this case, you also need to do some multiple theory, very elementary, but you also need to consider the case that the unipotent group, like 1, 1, 1, also defined over Q, and inside here, UZ is indeed a lattice theory for compact lattice. It's
So we dealt only with the semi-sample case.
So far we did only something, but this is general. This is
general.
This is general, and to deal with this is easy. It's 5-line argument. Margulis does it also all this multiple theory is very beautiful, but elementary. For I just say that to do this, to do the general case, we need to. So by the way, so there is some structure theory that tells you that any algebraic group, in particular every Q algebraic group, has a Levy decomposition as a direct product of let's say a reductive group, same direct product with unipotent. And so this is reductive, and this is unipotent. And
This is under what conditions?
every algebraic group has this is called sometimes the V decomposition.
Some
Maybe, yeah. Anyhow, so we need to deal with reductive group and with unipotent group. So first, it shows that GZ is commensurable to RZ semi-direct QZ, and then you reduce the case to reductive group and the unipotent group. The unipotent is on a few lines, and basically what is less trivial is to deal with same simple group which are not adjoint. So
But then there's also the from reductive to semi-simple. I mean,
yeah.
it's also something you need to.
Yeah, you need to deal with it, but to the reductive, which is anisotropic, yeah, so there's no Q character. So we do it. It's only 1 page or 1.5.
Okay.
Somehow I don't want to do it here. It's
And it's the Q characters should be also, the condition should be also necessary. Like it's if you have Q characters, then they assume you're not a lattice.
yes, because if you were, I mean, think of it. If you're, it's an X. Yeah.
Okay.
It's because, yeah.
And the connected condition is not really important, right? That should be
It's Q connected. There is Q connected.
Q connected. It is okay.
Yeah, it's. I mean, every algebraic group is only. You don't really need it.
Okay.
You know. So so this is about Borel and Chandra. So actually, I have time to solve the exercise for before if you want. The difficulty in this exercise is just to find the right notation. If you came up ready with names for the functions, Cij, and so on the thing. So do you want me to do that or maybe finish it? You happy if I did it? Anyone wants to do it? So the fact that if you have a Q isomorphism between two groups, then the image of the integer point is measurable to the integer point. So it's important, elementary, it's good to know. So, but I'll leave it a minute. And it's you can find it in Platon Rapid in other textbooks. Okay, so let's finish early so you can practice for the meeting. Be prepared for the meeting. So I think how many lectures do we still have? Two. So it's not a lot of time to discuss. So basically now we finished the first third. The first third of the plan was to discuss lattices and then to discuss invariant random subgroup and then to discuss non-invariant random subgroup. And we discussed lattices and semester is over. So I can either next year I'll give it a course mostly about random groups, but in these two remaining lectures I can either tell you about invariant random subgroups, or I can tell you more about lattices. So do you have any preference?
What do you do for the lattices?
I have to think.
Like general direction.
I guess it depends how far you can go. If you'll just waste all the tutors just to make the definitions and not show anything.
In fact, I can give this overview the same. How many of you attended my MSRI 3 lectures? Was 1.5. So maybe I do. I think these were nice lectures with the brief overview of invariant random subgroup, but I'll give some emphasis on open problems. But maybe some of you will be bored. That's one option. Another option is to present another result about lattices.
Can I question that lattices in specifically in P-adic groups?
Yes, the lattices in P-adic groups.